Hey, how are you going with models of growth? This is part 5. I've got a word up here and I don't know whether you're familiar with it. Exponential. Oh, exponents. That's powers, isn't it? 2 squared, 2 cubed, all of that stuff. Well, I wonder why that's important in describing growth. And we're going to spend the whole presentation here on looking at how exponentials does describe some forms of growth in everyday life. Okay, but first of all, an exponential curve's got a curve on it, and why? Here's my burning question here. What makes a curve curvy? Or also known as, why isn't a curve a straight line? Because we're going to look now at things that grow more rapidly than just in the linear model. They scoot right up, like this one here, or this one over here, a bit more quickly than a straight line that we've seen before. So there's the question, what makes a curve curvy? Because the exponential function, when we graph it, does have a fairly rapid increase, and things grow like that. So it's a good model. So I don't know whether you want to pause the presentation and use some of our rates of change from before, y step on x step, here it is down here, y step on x step, and compare that with the straight line. So pause the presentation, see if you can answer the question. What makes a curve curvy? All right, I'm going to answer it now. Let's try and do a y step over x step for a curvy dude. So if we came on here at the value 2, it looks like x is 4. If we go to the value x is 3, it goes up to 9. Hey, so a step of 1 is an increase here from 4 to 9 is a step of 5. Let's go up another 1 for x across here to 4, and it's gone up, what's the scale here? It's gone up to 16. So a step up of 1 in the x is now 16. Can you see what's happening? The rate of change, the y step, delta y on delta x, increases as x increases. Okay, so it's pulling it off straight. A straight line has a constant delta y on delta x. It's called the gradient, isn't it? Whereas this curvy line is actually, as you increase x, or change in x by 1, the change in y is getting greater and greater, so it's pulling it upwards. Hey, well that's interesting. It's going to be a very important way of thinking later on in your math career when you do something called calculus, looking at the rates of change of the independent variable or the dependent variable against the independent variable. All right. So have you got some idea of why that's going up like that? That's important. What we want to do now is to investigate that sort of function and then see where it's important in modelling. And here it is first of all. What is the exponential model and why is it important? Okay, well first of all, we can see the graph was a fairly steep one, the exponential model, but we still don't know what that is. But we'll answer this question first. There's a lot of things that go up in life like that. This could be a population of mice or something in weeks, and they multiply. They go up rapidly. The more there are, the more you will get, and as it goes along here, this delta Pn, change in the dependent variable over n weeks. Let's just start this modelling exercise now. We wouldn't have delta y on delta x here, would we? Because we're modelling, we're making a mathematical model of a practical situation. So we've got to come out of x and y land into the practical variables here, weeks and population of mice. So you can see it's going up more steeply than a straight line. And what's this over here? Grams of something with years. This is radioactive decay. Okay, so radioactive isotopes decay. Okay, and so here's our initial weight after a certain time. Here it's 3.2 years. They have a characteristic halving property here. So in a certain period, they always come down by a half. So this is from there, it's gone to there, and then to there. That's an interesting practical application, and giving us this curvy line, which is called, well, it's a graph of the exponential function, and that's what we want to investigate now. So let's do a little bit more with that and come down and have a look here at that population of mice, the original population. Let's say it's 100 mice, and it's growing at the rate of, what do we got here? 20% per week. So we multiply it by 1.2, going up by 20%. And then that value, that next value is again multiplied by 1.2. There it is there. Hey, this looks like what? This looks like a geometric sequence to me, back from the other form of modelling that we're looking at using sequences. Can you see the ratio is 1.2? What's the consequence of that? Well, it's going to go up by different amounts here each week. That's going to change ever so slightly, up by 20%. And so it's going to be a curve. It does not have a constant change in population with weeks. Okay, and here we have a general formula now, and you could have got that from sequence work as well, but here we're going to look at that as a function and draw its graph. We didn't graph them in sequences so much. Okay, getting the idea, different ways of modelling situations. And here's another one. Here's our radioactive material, radioactive isotope, 20 grams of it, and after each year it loses 5% of its weight, so we're going to multiply by 0.95. And we would have this, and then this, geometric sequence again, isn't it? This time it's got a fraction, 0.95, which is the constant ratio there, or the constant multiplier if you like. So what would our formula be? We could do sequence work to get that formula, or we could see it there, it's 20 by 0.95 to the end. Every time n increases by 1, you multiply by another 0.95. And here's its graph. All right, so it's coming down, and it's a decreasing function. Okay, so there are a few things around in the world which are nicely modelled by the exponential function. Okay, let's have a look more at that and see, and the screen clippings now from Hayes and Harris publications, so you should grab their book and have a look at it. So we're talking about functions like this. Okay, we've seen a couple there based on our idea of sequences, and they had a number out the front as well, timesing by the first term there. But let's just take the function where it's a power of some base here. And we're going to say for this discussion, A is going to be greater than 0. It's a practical model. If it was less than 0, if it was a negative, you might want to think what the graph would look like then. That's a bit more complicated. And A is not 1, because 1 to the x would just be a flat line, wouldn't it? 1 to any power is 1. Okay, so let's take this example, 2 to the x. Let's raise 2 to the 3, it's 8. 2 to the 2 is 4. 2 to the 1 is 2. 2 to the 0, any base raised to the 0 power except 0 itself is 1. 2 to the neg 1, hey, we might have to revise some power rules here. 2 to the neg 1 means 1 over 2 to the 1, or a half. 2 to the neg 2, remember negative powers or exponents? 1 over 2 squared, or a quarter. And here 2 to the neg 3 is 1 over 2 cubed, or 1 over 8. Okay, now you might say, gee, I've forgotten that. And in the next couple of presentations, we're going to look at going back and revising the rules so that you can work with these functions a little better. But at the moment, we're doing modelling, mate, and we want to see how this function can model these growths and decays that we might have around the place. So when you plot this, look at what you get. What's happening down here? It's getting smaller and smaller, isn't it? Okay, because this is 2 to the x, and this is negative, so it's 1 over 2 to a larger and larger power. Hey, that is going to tend to 0. Okay, and we call that approach to that line an asymptotic approach, or the x-axis, that is the y equals 0 line, is a horizontal, it's a flat line, a horizontal asymptote. Let's just watch the word there, asymptote. Okay, because it's a line that the graph approaches within a region. It gets closer and closer to it. Never meets it though, because no matter what you've got in the bottom line here, you've got some power of 2. It's going to make the bottom line huge. It's going to make 1 over a huge number 10 to 0, but it'll never get to nothing. It'll always be something left there, because you've got 1 divided by that. All right, so there's an interesting idea, and then we can have a look now at variations of this. We need to study this exponential function carefully because we want to use it for various different models. And we're going to vary A, and we're going to vary the number in front. If the population of mice started at 20, we'd have a 20 in there. Do you get the idea? Let's come down now. We'll just get rid of that. And let's come down now and have a look at a little investigation from Hayes and Harris Publications. I want you to go quickly through this. It won't take long because I've got a bit of work here with the Casio. You can use the graphing package from the publication if you wish, or I'm going to show you how to do it on the Casio. So what we're going to do is we're going to change A to the X. See what happens if we change that number in various ways. Okay, and then we're going to do various other changes. Down here, we're going to have 2 to the X, and then 2 to the X, added 1 on the end. Take 2. So lots of variations, and I want to show you on the Casio a bit of fun with how to draw these quickly. So turn your machine on here, and I want you to highlight Dyna. It means dynamic, and you're going to see a lot of graphs displayed in a moving fashion. And if you then hit execute, you get this entry window here, which looks like the ordinary graph entry window, but it's dynamic there. Okay, so make sure you've got that. Okay, so now you want to introduce another variable as well as seeing how the function changes with X. We're going to put another variable in here. See what I've done down here? A to the X. How do I do that? Well, I want you to do that. I want you to hit the alpha key here and then this button here, which brings out that little A. Okay, and then the hat in here for the power. There it is. The hat key there means the power, and then raise it to the X as normal. So we're going to have this up here, y equals A to the X. So you might have to pause the presentation and study those steps. What it means is I can put different functions in by varying the new variable A. Okay, let's do that. So now what we want to do is to hit F4 because I want to choose var. So hit F4 and we get this window. And we want to start at A is 1, so put in 1 there. And then hit the set button here, which is F2. And we get this here, dynamic setting. Tell it to start with an A of 1 and end with 5. So what does that mean that's going to do? It's going to have 1 to the X, well that's a bit flat, 2 to the X, 3 to the X, 4 to the X, and 5 to the X. And it's going to show you the graph flicking from one to the other. So it's going to be quite clear what the effect of that changing the base, the A, is going to be like. Then if we hit the speed, which is F3, okay, I haven't shown it on that window there, let's just come down. So here, if we exit that, you go to speed. Okay, we see it back up here, F3. And I think the best speed is the normal, so that's F3 again. We get that. You can slow it, you can stop and go it, you can slow it or you can speed it up. Now what happens when you hit execute? Well, see here? I've frozen the screen at 3 to the X. Y1 equals A to the X. So it's going to put 1 in, 2 in, 3 in. And this is the graph, what the graph looks like when 3's there. So that's going to help you, in a fun way, look at a range of variations in this exponential function. So come back up, and I want you to start now with these questions. There's question 1, 2, and 3. I want you to try to describe what's happening to the graph. You know why we want to do this, don't you? We want to try and get models for anything at any rate of increase, any mouse population, bacteria grow more quickly, or anything like that. We've got to manipulate our function so that we can model those various situations. Okay, pause the presentation, have a go. We'll just get rid of that. That's actually not true. So here, come down, and there's 4 and 5. So I want you to write some observations down in your notes there so that you will know how to model various types of growth. Okay, faster ones, slower ones, and change the model accordingly. All right, let's go on now and see what you were supposed to find. And we've just got a little summary down here. I'll just bring this down. Here we are. Okay, general exponential function. We've started to play with numbers in front, different numbers to raise to a power, taking something away from the power and adding something on the end. Can you see how powerful this model will be? Okay, because we can adjust to determine a best model, okay, just to obtain a best model for any situation that looks like an exponential growth. Okay, so that's what we're tooling up to do. Playing with our basic a to the x function, like 2 to the x, and being able to adjust it to model anything. Okay, did you find that b controls how steeply the graph increases? So, if b is between 0 and 1, that's a fraction, it's a decreasing function. It's halving or something each time. If b is greater than 1, it's increasing. 3 to the x increases more quickly than 2 to the x. 10 to the x is even quicker. C controls the horizontal translation. Just notice up here, if it's neg c, it moves plus c in the x direction, or in the horizontal direction. We've got to watch how often we use the words x and y now, because we're modelling, and it's probably going to be more like population and weeks or something like that, P and N from before. And D controls the vertical translation. So if you add D, it's going to move up the vertical axis D units. And also the asymptote, the line that it's flattening out to, is moving up. I hope you saw all of that. This is not a lot of new work in actual fact, because remember back to quadratics, y equals x squared, okay, back in your junior maths, and then we say, well, okay, if we put x take 2 squared plus 1, what happens? We looked at that before, and you can prove this, not in this course, but we could prove this one. X take 2 and move it across plus 2 and up 1, okay. So here, it's a plus 2 across there and up 1. So that vertex now, instead of being north north, is 2, 1. Do you remember that stuff? Because it's the same idea. Transformations on the plane, where we move all points plus 2 and plus 1 becomes the x value take 2 and then 1 added to the y. It's common to all functions. All right, so here we have the idea. If A is positive, that's the number out the front, and B is bigger than 1, it's increasing. If A is greater than 0, but B is a fraction, it's decreasing. If A is less than 0 and B is greater than 1, it's decreasing, but it looks like this, because the number out the front is negative. Did you find that? And then it's a fraction, it's going to be increasing. So these change around. Okay, so B is greater than 1, but you're multiplying it by a negative out the front, so it's going to become more and more negative. Let's take an example of that. Y equals what? Neg 2, oh no, sorry, I've got to put, yep, neg 2, that'll do, and then 3 to the x. So as that gets bigger, this gets bigger, but this makes this more and more negative. So it's going to go down, so it's decreasing, even though b is greater than 1, if you put a number in front there. So here, if it's y equals neg 2, and then a half to the x, okay, it becomes less and less negative. It's increasing, because this will make the number less and less. It'll come up, from more negative. There's down low. It's going to come up. It's actually decreasing here, becomes increasing, because your fraction is usually a decreasing effect, but you're starting off in negative land, so it's going to become less and less negative. Try and get your head around that. Play with the calculator again with that. Maybe with a table of values even. All right, are you getting your head around how to play with this function? Here's a chance. We're going to do some modelling in a minute, but just for the moment, we're trying to gear up with understanding the function. Okay, so here we're trying to read off from the graph. So, for example here, 1.8 on the x-axis means 2 to the 1.8 would be that number there. Just make sure what you understand by a graph of 2 to the x. If you put an x value in there, you'll get the value of 2 raised to that power. So you can read a couple off here and check to see with the answers down underneath here how you went. Okay, so try question 1. Get your head around what that graph is doing. And then we'll go to question 2, 3 and 4. Draw freehand sketches of the following pairs using the idea of transformations and what you did before. Okay, just keep in mind, what does a number out the front mean? Okay, substitute x is naught in for the x value there and see where that function would start. Okay, and then check it with technology. All right, in question 4, we have a graph already drawn, and you're supposed to sort of copy that and then see if you can work out what changes each of these would have on the, what effects they would have on the graph. If you put 3 to the neg x, where does the graph go? You might actually have to use technology for a couple of those. All right, see what you think. I'll show you the answers now. Here they are. So some interesting ones here. Just keep in mind what you're doing. So here, 2 to the x and multiply by negative reflects it in the y-axis. Let's go down and do a couple more. 2 to the x and 2 to the x take 2. Okay, so 2 to the x, everything's moved across 2 units. Okay, everything's moved across 2 units. And now it's cutting there a quarter, because if you put x as naught in the equation, that will be the y-intercept. All on the y-axis, x is naught. Okay, look at the effect of the 2 here. There it is there. All right, let's keep going. Question 4. 3 to the x, and you multiply it by negative. So all the values have gone over there. A reflection in the y-axis. Okay, study them carefully. 3 to the x plus 1. Being moved up 1. New asymptote. Okay, 3 to the x, neg 3 to the x. Okay, so here it's been reflected down here. And 3 to the x take 1, moved across by plus 1. Everything's moved across. So new y-intercept there. Okay, and let's go and do some more. Okay, so we're going to start talking about the various properties of this graph, and we'll have to go back later on and make sure you can handle exponents or powers. So here's a graph again of an exponential function, and I think this one's been translated up, hasn't it? Okay, because it looks like the asymptote is at 1. Y equals 1 is the new asymptote. So what we're going to do is take our basic function and see if we can work out properties of it. So you can see here we've added 1, everything's gone up. So y equals d is or 1 is the new horizontal asymptote. And this dude here is saying all of them are similar because they all come from that basic form, and you have to look at their key properties and get a reasonable graph. So you could work out the horizontal asymptote, see what's been added down the end here. Put a line through there. We usually put a dashed line to show that the graph is approaching it. The y-intercept, how do you find that? Substitute x is naught in the equation. and then maybe sub in a couple of other x values and draw a couple of points. So you've got it reasonably well. So x is -2 and x is 2. So you've got something to swing through there. And then you can get a reasonable graph by hand without technology. And it enhances your understanding. Okay, so just remember these. Horizontal asymptote, what's the line that the graph now approaches, because there's been a translation in the y direction. The y-intercept, and sub 2 points in. Okay, let's go down and try some. Here's an example again from Hayes and Harris. So sketch the graph of y equals 2 to the neg x, take 3. Okay, first of all, we see this has been moved down -3, so that's the new asymptote. Substitute x is 0, so it's 2 to the 0, take 3. 1 take 3 is -2. So let's put that on there. -2, asymptote down at -3. Sub in 2, 2 to the -2, take 3. It's quarter, take 3, is -2 3/4. So that's this point over here. And then when x is -2, this becomes 2 to the +2, take 3. 4 take 3 is 1. So that's up there. So it's as we would expect. It's coming down that way. Why? Because we had neg x in there. And if you put a neg x in there, it's a translation of the original graph. Let's try and draw the original graph now. The original graph would have been like that. 2 to the x. By putting in neg x there, we're going to reflect it in the y-axis, and it's going to come down, oops, like that. Okay. Then we subtracted 3. So then it's down here, and that asymptote is down there, like that. Okay, so that's what's happened. Just remember, 2 to the neg x is a reflection in the y-axis. It goes over the other side here. All right, let's have a look now at doing some. So here you are, sketch some graphs of these. Okay, try and do it by hand. You can check it with technology, or I'll show you the answers now. 5A, B and C. Let's have a look at D. And let's go on. Do another one. We're coming up to some modelling now. We're getting familiar with our function, so let's see if we can apply it and use it to describe a practical situation. Okay, an entomologist studies cropping creatures like grasshoppers and other insects. I think it's insectology, I don't know. Okay, monitoring a grasshopper plague. Notice the area affected is that, so he's made a model. Okay, so here, that's the area in hectares. So there's the initial number of hectares, and this is after n weeks. So find the original affected area, and then the affected area various times, and let's plot out what's happening. Because these little fellas multiply very quickly and move around quickly. So the area affected is 1,000 initially by 2 to the 0. Because initially means when time is 0, when he started measuring. So it's 1,000 by 1, it's 1,000 hectares was originally affected. After 5 weeks, so you can put 5 in there, and 0.2 times 5 is 1. And put 2 in there, here, so 10 in there, so 0.2 to the n is 0.2 times 10 is 2. So it's jumped up 2,000 and 4,000. You can see this multiplier effect, the ratio of the sequence, if you wanted to relate it back to that, is bigger than 1, so it's doubling. Okay, so after 12 weeks, 0.2 times 12, 5,278. So it's really jumped up in the 12 weeks, and that's what we're worried about with plagues like that. And this is because, let's study the function, n equals 1,000 by 2 to 0.2n. Can you see this number is bigger than 1? So therefore it's going to increase quickly. it's a number bigger than 1, it's going to, every time you change n, it's going to have a power of 2, which is 2 to the 0.2n. Okay, n getting bigger means going to multiply by a higher power of 2. Let's have a look at the graph. It's typical exponential, so it's a good one for this modelling exercise. Just remember here, can't have x and y. You must have it in the context of the practical situation. Must have a scale here, and here we should have hectares, yes, units, and here weeks, and label carefully. Don't assume that each division is 1. It's not here, it's 2s. And up here the divisions are 2000s. So it must all be labelled. That's very important. That in final exams and things, this is usually worth 3 marks, this graph. There's only 1 for all the scale and labellings. Then there's 1 for the key features. Okay, get a couple of key features in there, and then a shape. So you need to be careful and try to be pretty precise here with this graph. All right, let's go down now and have a look at doing some. So here we are, question 1 and 2. They do the same thing. Okay, you use technology as well, but in exams you sometimes are asked to actually draw a graph, so you need to do it by hand as well. Let's look at question 3. Okay, and question 3 and also question 2 have got this idea of V0 and P0 in them, so you've got to think about that. P0 means the population at the start at time 0, so that would be t is 0. Okay, so try to get your head around that a bit. I'll leave you to think about that one. Let's look at the answers then. Okay, to 1, 2 and 3. Okay. Percentage increases there, you might have to look carefully at that. All right, let's go down and look at another application. So here's radioactive decay I showed you before. Okay, so there we have it. We have the graph, and here we're talking about the sequence. You could do it with a sequence. And the idea here is this is the next application that we want to use for the exponential function. The idea that it is some base raised to a power. In this case it's a fraction, so it's going to be a decreasing function. It's a decreasing function. Let's just look at that. As we go from, let's say, this time 10 to time 20, we have what? We've got this decrease here. So that actual rate of change there would be negative. As the independent variable increases, the dependent variable is decreasing. That's going to be important later on in calculus, where we're looking at the rates of change of one variable with respect to the other. And of course we always talk about how the independent variable changes and what response or dependence we have from the other variable upon that. So this would be a decrease, and so it's a negative rate of change. All right, very good. Let's go and have a look at some more. Okay, here we are. Half-life, this is getting a bit more detail, and you saw this earlier where I drew this, and the idea is that a half-life is a characteristic of radioactive material. It's the time required for it to decay to 1/2 of its original value. Okay, so what we've got here is, if we had weight and time, if this was some W0 means a starting weight at time 0, that subscript means a starting weight, and then this is always constant, time for it to halve. Okay, so the idea here is that we could actually graph it without a formula. We could use the graph alone as a mathematical model. Remember, a mathematical model is a mathematical description of a practical situation. It could be a graph, a formula, a table, a sequence. Okay, so let's try and use exponentials now to model that situation here. So here's a weight of radioactive material type problem. We start off with this formula that's already been constructed from, let's say, measuring this material over a period of time. Find the original weight, same stuff again, weight after a certain time, and then graph it. So if you substitute t as 0 in there, that will be the original time, so the weight will be the 11.7 times 2 to the 0. Then putting in 10, and here 100 and 1,000 for t. Just remembering you've got neg 0.0067 times t. Okay, and plotting these are a bit hard to plot. Wouldn't bother too much because of these huge scales here, but you should be able to get somewhere with it. Make sure you get the starting value. We've got a couple of other points, and then it's an asymptote to the t-axis there. Just remembering you must look at using maybe x and y with technology, but when you come back and applying it to a practical situation, please use modelling ideas, and that is change the variables to the context of the question. Okay, let's look at 2d5, question 1 and 2. Same ideas, just going through and getting familiar, so don't spend too much time on that. Let's have a look then at the answers to that. Graph should look like that. Do you agree? Can you start to see now what's going on and how you can adjust your model? All right, let's go to the last little bit now. And this has got an important point right on the end, so I might have to revise some percentages here. We've got a model again. This time it's a generic model. It's saying this radioactive material always behaves like this, and we could put in a different starting weight. So W0 is a generic starting weight, if you like. W at 0 time means I might start with 10 grams, you might start with 20. Okay, so put that in there. So find the original weight. So put t as 0, and we see that the idea of W0 implies the weight at 0 time. Weight at time 0. Okay, so it's a starting weight. So it's a symbol. It doesn't mean W times 0. That subscript labels it, as in sequences, it labels it as the weight at the start when the time is 0. Okay, now find the percentage remaining after 200 years. Ooh, let's find what the weight is after 200 years. So sticking it in there, we get this creature. Look at the approximate sign, because 2 to that power is going to be irrational, it's going to keep going. So we've got that. What do you do with that? Now, the percentage remaining, well, can we interpret this? We don't know the actual weight because we didn't know the starting weight, so this is a generic statement. We've got 0.8706 of the original. Now, the original was one lot of W0. We've only got 0.8706, change it to a percentage, multiply by 100. That means we've got 87.06% of W. And generally, you would change this in this course to 3 significant figures and quote that there. Okay, so get the idea. You can work in generic land, and it's important to see that the value of that is anybody can use the basic mathematical model and put in their particular numbers. But they'll all lose in that time 13% or whatever, 12.94%, you'd have 87.06 remaining. Okay, get your head around that and come and practice it now, and we'll finish there. Okay, so here's 3 and 4. Look at trying to work with these, if you like, generic starting points here and work through. Okay, let's have a look now at the answers to those. And here we are, question 3 and 4. Okay, see what you think there. And we'll just finish off with a little bit down here. And here's the last one, last little example here from Hayes and Harris. So radioactive substance, 20 grams and a half-life of 3.2 days, very active here. Sketch the graph, find the equation. Okay, so sketching the graph, you can start at 20 and do it by steps. At 3.2 days, come down to 10, 6.4, another 3.2 days, 5. So that's another way of approaching modelling. If you know that data, you can, here, we've got this information here, you can draw the graph, and then we can fit the general function. So here we could say, we don't come out of y and x land, mate, that's mathematics, we want to use it to model in the context of the question. So y would be wt, and x would be t, and now we've got to fill in these two variables, a and b. So here when t is 0, we know that the weight is 20, so it becomes wt equals 20 by b to the t. Or they've put it there, a, b to the 0, so a is 20. And then putting in t is 3.2, we know the weight is 10, and so we can put that in and come down, oops, hang on, I messed that up a bit, so come down here, and we find that b, retracing b, and b is not a nice whole number, as you'd expect that with modelling. Nature isn't going to be perfectly whole numbers all the time. You can test that by measuring one of your fingers is exactly 2.5 or 5 centimetres long, or something like that. Is it? No, it's going to be a decimal. Natural variation there. So we have our model, and we may well use 4 figures here and round the answer to 3 at the end of applying that model. All right, you get the idea. Be flexible, get up close and personal with the exponential, because it's a powerful modelling tool later on. Okay, so here we are, question 5, 6 and 7. And I think this is important for your later experience in maths. Question 7, trying to structure a model from, what, a starting value and 1 point on the curve. Can you do it by substituting in as we just did above? All right, pause it, have a go, and I'll show you the answers now. Okay, so there's the last bit. See how you went, and talk to your classmates and teachers about that. What we're going to do is to go back and just hone up your skills a bit. We're working with powers, because we want to do things with the model once we've gotten it now, and we want to put it equal to things and solve equations and stuff like that. So there's some presentations coming up. Get rid of this one. Presentations coming up. But for now, it's cheers from me.